A powerful storm system is now entering a critical phase across the United States, and instead of following a single path, it is beginning to split. This is where the forecast becomes more complex and more dangerous. Two separate impact zones are now forming, each carrying different types of weather threats. One path is pulling colder air deeper into the system, while the other is feeding off warm, unstable air. That split is the key to what happens next, because depending on which side of this divide your region falls into, the impacts could be completely different, from heavy rain and severe storms to strong winds or even winter weather. Why the storm is dividing. Storm systems do not always follow a simple straight path across the country. While many people expect storms to move in one clear direction, the reality inside the atmosphere is far more complex. The movement of a storm is controlled by winds at different levels of the atmosphere, and when those winds begin shifting in different directions, the storm itself can start to change shape and behavior. That is exactly what is happening with this system right now. At higher levels in the atmosphere, strong winds are acting like steering currents. These winds guide where the storm travels and how quickly it moves. In this case, those upper-level winds are no longer aligned in a single direction. Instead, they are beginning to split, with one stream of faster-moving winds pulling part of the storm toward the northeast, while another set of winds allows a separate portion of the system to continue moving more directly east. When this type of wind pattern develops, it creates a stretching effect within the storm. Instead of remaining compact and moving as one unit, the storm begins to elongate across a wider area. As it stretches, different parts of the system start responding to different atmospheric forces. Over time, this leads to the separation of the storm into two distinct branches, each following its own path. This process is often influenced by what meteorologists call the jet stream, which is a fast-moving ribbon of air high above the Earth's surface. The jet stream does not always flow in a straight line. It can curve, dip, and split into multiple segments. When a storm system interacts with these changes in the jet stream, it can become caught between different flow patterns. One portion of the storm may become embedded in a faster-moving segment of the jet stream, while another part lags behind in a slower-moving flow. As this separation continues, each branch of the storm begins to develop its own characteristics. The northern portion may be influenced more by colder air and faster winds, while the southern portion may remain connected to warmer, more humid air. These differences further reinforce the split, making it more likely that the storm will continue evolving as two separate systems rather than merging back together. It is important to understand that this type of division does not mean the storm is weakening. In fact, in many situations, a splitting storm can become more impactful because it spreads its energy across a larger geographic area. Instead of concentrating all of its effects in one location, the storm is now capable of influencing multiple regions at the same time. This wider reach means that more communities may experience some form of weather impact as the system progresses. One area might deal with heavy rainfall, another with strong winds, and another with colder conditions depending on which side of the storm they are located. The separation essentially creates multiple zones of activity, each with its own weather pattern. Another key factor contributing to this division is the difference in air masses across the country. Warm, moist air is still present in some regions, while cooler, drier air is pushing into others. As the storm interacts with these contrasting air masses, it becomes more difficult for it to maintain a single, unified structure. Instead, it adapts to the environment around it, allowing different sections of the storm to evolve independently. This is why meteorologists are paying close attention to how the storm is behaving right now. When a storm begins to divide, forecasting becomes more complex. Small changes in wind direction or temperature can influence how each branch develops and where it ultimately travels. A slight shift in the upper-level winds can change the position of the dividing line, which in turn can alter which regions experience the most significant impacts. As the system continues moving, the separation may become even more defined. Each branch can strengthen under the right conditions, especially if it continues to draw energy from the surrounding atmosphere. This means that instead of one storm weakening over time, there may be two active systems affecting different parts of the country simultaneously. The key takeaway is that this storm is entering a more advanced and dynamic phase. It is no longer a single straightforward system. It is evolving into a more complex structure shaped by shifting winds, varying temperatures, and changing atmospheric conditions. This evolution is what allows it to extend its reach and impact a broader region as it continues moving across the United States. The northern path. Colder and more intense. As this storm system begins to divide, the northern branch is evolving into a colder and more concentrated side of the system, and this is where conditions can become more intense in a different way. This portion of the storm is drawing in colder air from the upper Midwest and the Great Lakes region. and that colder air is beginning to wrap around the system as it moves. When this process begins, it changes not only the temperature profile of the atmosphere, but also the type of precipitation that reaches the ground. In areas along this northern path, temperatures are lower both near the surface and at higher levels in the atmosphere. Because of this, precipitation that might have fallen as rain earlier can begin transitioning into snow or a mix of snow, sleet, or freezing precipitation. This transition zone is often one of the most sensitive parts of a storm because small temperature differences can change conditions quickly. A slight drop in temperature can turn rain into snow, while a slight increase can keep precipitation in liquid form. As colder air continues feeding into the system, snowfall becomes more likely across portions of the northern track. However, snowfall alone is only part of the concern. Winds within this branch of the storm are also beginning to increase as the pressure gradient tightens. The pressure gradient refers to the difference in atmospheric pressure across a region. When that difference becomes stronger, air begins moving more rapidly, resulting in stronger winds. These winds can significantly enhance the overall impact of the storm. Even when snowfall amounts are not extremely high, gusty winds can reduce visibility by blowing snow across roadways and open areas. This creates conditions where it becomes difficult for drivers to see clearly, especially during periods of heavier snowfall. Snow that has already fallen can also be lifted back into the air by the wind, creating blowing snow that further limits visibility. Another effect of stronger winds is the formation of drifting snow. As wind moves snow across the surface, it can accumulate unevenly, creating deeper drifts in certain locations. Roads that may have been cleared earlier can quickly become covered again if snow is blown back across them. This makes travel more challenging, as conditions can change rapidly even after snowfall has stopped. In addition to reduced visibility and drifting snow, colder temperatures along this northern path can also lead to icy conditions. When temperatures remain near or below freezing, moisture on roads and surfaces can freeze, creating slick conditions for both drivers and pedestrians. Bridges, overpasses, and untreated roadways are often the first places where ice forms because they lose heat more quickly than other surfaces. The combination of cold air, snowfall, and increasing winds creates a more complex weather situation. Each element on its own can cause disruptions, but when they occur together, their effects become more noticeable. For example, moderate snowfall that might normally cause only minor travel issues can become much more disruptive when combined with strong wind gusts and freezing temperatures. Another important factor is the duration of these conditions. As the northern branch continues moving, areas along its path may experience extended periods of cold and precipitation. Even if snowfall rates vary, the persistence of these conditions can lead to gradual accumulation and continued travel difficulties throughout the event. Meteorologists are watching this northern path closely because it represents a zone where conditions can intensify in ways that are not always immediately obvious. While heavy rain or severe storms may draw more attention in other parts of the system, winter weather impacts can develop steadily and create significant disruptions over time. As this branch continues to evolve, the interaction between cold air and incoming moisture will determine how precipitation develops. Areas located within this colder portion of the system should expect changing conditions as temperatures fluctuate and precipitation types shift. Even small changes in atmospheric conditions can influence how the storm behaves along this northern track. The northern path represents a colder, wind-driven side of the storm system, where visibility, road conditions, and travel safety may all be affected. As the system continues moving, this branch will remain an important area to monitor, especially for regions that may experience a combination of snowfall and gusty winds throughout the duration of the storm. The southern path, warm, unstable, and active, while the northern side of the system is drawing in colder air. The southern branch is evolving in a completely different environment, one that is warmer, more humid, and far more unstable. This contrast is what makes the storm split so important, because each side behaves differently based on the air mass it is connected to. Along the southern path, the atmosphere is being fueled by a steady flow of warm, moisture-rich air moving in from the south. This type of air mass contains a high amount of energy, and that energy plays a major role in how storms develop and intensify. Warm air near the surface is naturally buoyant, which means it tends to rise when conditions allow it. In this situation, that rising motion is already underway. As the warm, humid air lifts upward into cooler layers of the atmosphere, it begins to condense and form clouds. When this process becomes strong enough, it leads to the development of thunderstorms. Because the air contains so much moisture, these storms can grow rapidly and become more organized compared to weaker, less energetic systems. This is what meteorologists refer to as an unstable atmosphere. In simple terms, instability means the air is ready to rise and continue rising once it gets started. The more unstable the atmosphere becomes, the easier it is for storms to form and strengthen. Along this southern path, that instability is being supported not only by moisture, but also by temperature differences between the surface and the upper atmosphere. These differences create a strong upward motion that helps storms build vertically and sustain themselves. As storms develop in this environment, they often do not remain isolated for long. Instead, individual storm cells can begin interacting with each other, forming clusters or lines of thunderstorms. These organized structures are capable of producing more consistent and widespread weather impacts compared to single storms. Once storms connect into a line, they can move more efficiently across the region, carrying their impacts across multiple areas. One of the primary concerns within this southern path is heavy rainfall. Because the atmosphere contains such a high level of moisture, storms are able to produce intense downpours over short periods of time. Rainfall in these situations does not always fall steadily. Instead, it can arrive in powerful bursts, where large amounts of water fall quickly. This type of rainfall can lead to rapid accumulation on roads, in low-lying areas, and in locations where drainage is limited. Lightning is another common feature of storms in this environment. As strong updrafts develop inside thunderstorms, electrical charges build within the clouds. These charges eventually release as lightning, which can occur frequently during more active storms. Lightning is often a sign that the storm is well developed and actively producing strong internal motion. Wind is also a significant factor along the southern path. Thunderstorms in unstable environments can generate strong downdrafts, where air rushes downward and spreads outward when it reaches the ground. These downdrafts can create sudden bursts of wind that may arrive quickly and move across the landscape with little warning. In organized storm lines, these wind gusts can become more widespread, affecting larger areas as the system moves. Another important aspect of the southern branch is that it continues to draw energy from the surrounding atmosphere as it moves eastward. The constant supply of warm, moist air allows storms to remain active rather than weakening quickly. As long as this energy source remains in place, storm activity can continue expanding into new regions. This means that areas currently outside the storm zone may still experience storms later as the system progresses. Because the southern path remains connected to this energized environment, it is often the part of the storm system that shows the most ongoing development. New storms can form ahead of the main system, while existing storms may strengthen as they move into more favorable conditions. This continuous cycle of development allows the storm activity to persist over a longer period of time. Meteorologists are watching this southern branch closely because it represents the most active and dynamic portion of the storm. The combination of warm air, high moisture levels, and atmospheric instability creates an environment where storms can develop quickly and produce noticeable impacts. As the system continues moving east, this active zone is likely to shift into new areas, bringing thunderstorms, heavy rainfall, and gusty winds to communities along its path. In contrast to the colder, wind-driven conditions along the northern path, the southern side of the storm is defined by energy, movement, and ongoing storm development. It is this contrast between the two sides that highlights how complex and widespread this system has become as it continues evolving across the United States tonight. Where the split creates the most risk, the most critical area to monitor in a situation like this is not only along the individual northern or southern paths, but the region where both sides of the storm begin to interact with each other. This transition zone is where the atmosphere becomes especially sensitive and where even small changes in conditions can lead to noticeably different weather outcomes. It is often within this narrow corridor that the most uncertain and rapidly changing conditions develop. In this zone, the influence of colder air from the northern branch meets the warmer, more unstable air from the southern side. These competing air masses create a delicate balance in the atmosphere. A slight shift in temperature, even by just a few degrees, can determine whether precipitation falls as rain, becomes heavier, or transitions into a different form entirely. Because of this, the weather in these areas can change quickly and sometimes unexpectedly. One of the main reasons this region carries higher risk is because the atmosphere is already close to a tipping point. When conditions are this finely balanced, even minor adjustments in wind direction or temperature can push the system in a different direction. For example, if slightly warmer air moves into the region, rainfall may intensify and become more widespread. If cooler air pushes in instead, the same area could see a change in precipitation type or a reduction in rainfall intensity. Another factor that increases the risk in this transition zone is the way storms can organize more efficiently. When the northern and southern influences begin to overlap, the atmosphere can create stronger lifting motion. This enhanced upward movement allows clouds to grow more rapidly and can help thunderstorms become more structured. As storms organize, they often become more capable of producing consistent rainfall and stronger wind gusts. Wind patterns in this area can also become more complex. As the storm system tightens and adjusts to the competing air masses, wind speeds may increase and directions may shift over short distances. This can lead to sudden changes in surface conditions, especially when gusty winds develop alongside active storm cells. These shifts can occur quickly, making it more difficult to anticipate exactly how conditions will evolve from one hour to the next. Another reason this zone is closely watched is because it is often where forecast models show the greatest variability. Weather models rely on data to predict how storms will behave, but when conditions are highly sensitive, different models may produce slightly different outcomes. This leads to a wider range of possible scenarios for what might happen in these areas. Meteorologists must then analyze multiple sources of data to determine which scenario is most likely. Because of this uncertainty, forecasts in the transition zone are often updated more frequently. As new data becomes available from radar, satellite, and atmospheric observations, meteorologists refine their predictions to better understand how the storm is evolving. This constant updating reflects how quickly conditions can change when two different storm paths begin influencing the same region. Another important aspect of this area is how impacts can escalate quickly. Conditions may begin with light or moderate rainfall, but as the system strengthens or shifts, rainfall can intensify within a short period of time. Similarly, winds that start out mild may increase as the pressure gradient tightens across the region. This progression can make the situation feel as though it is changing rapidly, even if the storm has been developing for several hours. Communities located within this transition zone often experience the most dynamic weather conditions because they are positioned between two different atmospheric influences. While one side of the system brings colder, more stable air, the other side delivers warmer, more energetic conditions. The interaction between these two forces creates an environment where weather patterns are less stable and more prone to change. Because of these factors, meteorologists emphasize the importance of monitoring this region closely throughout the event. Identifying where this transition zone is located helps forecasters understand where the most significant changes may occur. It also allows them to provide more targeted updates as the storm evolves. As the system continues moving, this zone may shift eastward along with the rest of the storm. Areas that are not currently experiencing these mixed influences may enter the transition zone later as the storm progresses. This means that the region of greatest uncertainty and potential risk is not fixed in one location, but moves with the system over time. In situations like this, awareness becomes especially important because conditions can change quickly and forecasts may be adjusted as new information becomes available. Staying informed helps communities better understand what to expect. The transition zone remains the most sensitive part of the storm system, where the interaction between two different paths creates the potential for rapidly evolving weather conditions. Timing and movement tonight. As this storm system continues evolving tonight, one of the most important factors to understand is how its movement will unfold over time. Because the system has now split into two separate branches, its forward motion is no longer uniform. Instead of a single storm moving at one steady pace, there are now two distinct parts progressing eastward at slightly different speeds, each influenced by its own set of atmospheric conditions. The northern branch of the storm is being guided by stronger winds higher up in the atmosphere. These upper-level winds act like fast-moving currents that can pull storm systems along more quickly. As a result, the northern portion of the storm may begin to move at a faster pace compared to the rest of the system. This acceleration means that areas located along the northern path could experience earlier impacts, with conditions changing more rapidly as the system passes through. In contrast, the southern branch is behaving differently. This part of the storm remains connected to a warmer and more moisture-rich environment, which allows it to stay active and continue developing as it moves. Instead of simply being pushed forward, the southern side of the system is also growing and expanding as it feeds on this available moisture. Because of this ongoing development, its movement may appear slower, not necessarily because it is stationary, but because new storm activity continues forming along its path. This difference in movement between the two branches creates a staggered timing pattern across the country. Communities located farther west along the storm's path may already be experiencing impacts, while areas to the east are still waiting for the system to arrive. As the storm continues progressing, new regions will enter the impact zone gradually rather than all at once. For many locations, the first sign of the approaching system may be an increase in cloud cover. Skies that were previously clear may begin to turn overcast as the leading edge of the storm approaches. This is often followed by strengthening winds, which signal that the pressure pattern in the atmosphere is beginning to shift. Eventually, precipitation arrives, which may take the form of rain, thunderstorms, or other types of weather depending on the specific branch of the storm affecting that region. Because the system is so large, timing will vary significantly from one location to another. Some areas may experience storm activity early in the evening, while others may not see conditions change until much later at night. In certain cases, regions located farther east may not enter the storm corridor until the overnight hours or even into the early morning period. Another important aspect of the timing is that impacts may not occur all at once in any given location. Instead, weather conditions may develop in phases. An area might first experience light rain or increasing winds, followed by a period of heavier precipitation or more active storm conditions. After that, conditions may gradually weaken as the system continues moving eastward. This sequence can make it feel like the storm is building in intensity over time rather than arriving suddenly. The expanding nature of the southern branch adds another layer of complexity to the timing. As new storms develop along this path, areas that were initially expected to remain outside the main impact zone may still experience storm activity later in the night. This means that the reach of the storm may extend farther than originally anticipated, especially in regions where moisture and instability remain high. Meteorologists are closely tracking the movement of both branches using radar and satellite imagery to determine how quickly each part of the system is progressing. By analyzing these trends, they can estimate when specific regions are likely to experience changes in weather conditions. However, because the storm is evolving as it moves, these timing estimates may be adjusted as new data becomes available. Another key point to consider is that the transition zone between the two branches may also shift as the system progresses. This means that areas experiencing one type of weather early in the night could see different conditions later if the boundary between the two paths moves. This adds to the importance of staying updated as the storm continues to develop. The timing of this storm is not fixed or uniform. It is a dynamic process shaped by the interaction of two separate branches moving at different speeds and responding to different atmospheric influences. As the system continues pushing eastward, its impacts will spread gradually across the country, reaching new areas throughout the night. Understanding this staggered movement helps explain why weather conditions may feel calm in one location while becoming active in another. It also highlights the importance of monitoring updates, as the timing of impacts can shift depending on how the storm evolves. As the night continues, more regions will enter the storm corridor, each experiencing its own sequence of changing conditions as the system passes through. Why this system is being watched closely. Storm systems that begin to divide like this one are among the most closely monitored situations in weather forecasting, not because they are rare, but because they introduce a high level of uncertainty and rapid change. When a storm follows a single, consistent path, forecasting tends to be more straightforward. But once a system starts splitting into multiple branches, the atmosphere becomes far more complex, and even small adjustments can lead to noticeably different outcomes across the map. One of the main reasons meteorologists are watching this system so carefully is because the position of the dividing line between the two paths is not fixed. It can shift as the storm evolves, influenced by subtle changes in temperature, wind direction, and atmospheric pressure. These changes might seem minor on a large scale, but they can have a significant impact on what people experience at ground level. For example, a slight shift of the storm storm track by even a short distance can move the boundary between the colder northern air and the warmer southern air. When that happens, a region that was expected to receive steady rain might instead experience heavier rainfall or more organized storm activity. In other cases, areas near the colder side of the system might see a transition from rain to snow or a wintry mix if temperatures drop just enough. These types of changes can occur quickly, sometimes within just a few hours, which is why continuous monitoring is essential. Another factor that increases the importance of tracking this system is how each branch can evolve independently once the separation becomes more defined. In the early stages of a storm split, both parts are still somewhat connected, sharing energy and moisture. But as the division becomes stronger, each branch begins to respond more to its own surrounding environment. This means that one side of the system can strengthen while the other behaves differently, depending on the conditions it encounters. The northern branch, for example, may continue interacting with colder air and stronger upper-level winds, while the southern branch remains connected to warmer, more humid air that supports ongoing storm development. Because these environments are so different, each branch can intensify in its own way, producing different types of weather impacts across separate regions at the same time. Meteorologists rely on a combination of tools to understand how this split is evolving. Weather radar provides real-time information about precipitation intensity and storm movement, allowing forecasters to see where rainfall is increasing or where storm clusters are organizing. Satellite imagery offers a broader view, showing how cloud structures are expanding and how the overall storm system is changing shape as it moves across the country. In addition to these observations, atmospheric data collected from weather balloons and surface stations helps meteorologists understand conditions at different levels of the atmosphere. This information is critical because the behavior of the storm is largely influenced by what is happening above the ground, not just at the surface. Wind patterns, temperature gradients, and moisture levels at higher altitudes all play a role in determining how the storm will evolve. Computer forecast models also contribute to the analysis by simulating possible future scenarios. These models use current atmospheric data to predict how the storm might develop over time. However, when a storm is in a splitting phase, different models may produce slightly different outcomes, reflecting the uncertainty in how the system will behave. This is why forecasts are updated frequently as new data becomes available. Another reason this system is being watched closely is the number of people located within its potential impact zones. Because the storm is divided into two separate paths, it is capable of affecting a larger geographic area. Communities that might have been outside the main path of a single storm may now find themselves within one of the two branches. This increases the importance of accurate and timely forecasting. As the system continues to evolve, meteorologists are paying close attention to how the dividing line shifts and how each branch develops. The goal is to identify where conditions may intensify and to provide updated information to the public as quickly as possible. When storms behave in this way, the situation can change from one hour to the next, making real-time monitoring especially important. The reason this system is being tracked so closely is because of its dynamic nature. A splitting storm is not a static event, it is constantly adjusting to the surrounding atmosphere. Each branch has the potential to strengthen, expand, or shift direction, and those changes can directly influence the type and intensity of weather experienced in different regions. By continuing to analyze radar data, satellite imagery, and atmospheric measurements, meteorologists aim to stay ahead of these changes and provide the most accurate forecast possible. This ongoing process helps ensure that communities receive the information they need as the storm continues to divide and move across the United States. Right now, this storm is no longer following a single path. It is dividing, and that means two different weather stories are unfolding at the same time. What matters most is which side of the system your location falls into, because that determines what you experience next. Stay aware of updates, watch how the system shifts, and be prepared for changing conditions as the storm continues moving across the country. We'll keep tracking both paths and bring you the latest updates as this system develops. Stay informed, stay ready, stay ahead of the storm.